Okay, our problem is 319. First, read the problem. The cords BCA and CD can each support a maximum load of 500 newtons. Determine the maximum weight of the crate that can be hoisted at constant velocity and angle theta for equilibrium. Now we have the crate load at point A, which is connected with a cord or a string, so whatever it is, and then it is hoisted, so lifted upwards with a system here, with a pulley and engine. Well, the cord BC makes an angle of 513 12, sorry, not 13, 512 13, and the chord CD makes an angle of theta. CA is vertical and it is lifted, the load is lifted at a constant velocity, so the acceleration is 0. Therefore we can assume that it's under static equilibrium, and we are asked for the maximum weight that can be lifted by the system, because each cord has a strength of 500 newtons. Okay, so if the load in any of the cords exceeds 500 newtons, it will fail, the system will fail. Okay, now first we will begin by drawing the free body diagram. Of course, in this problem we will consider the junctions A and C as particle. So we will assume that they do not have any geometry, and we will write the equilibrium at point A and at point C in order to solve the problem. Let's begin by drawing the free body diagram at point A. So at point A we have the weight of the object. If we assume that, so let's assume that horizontal axis is x, sorry, and vertical one so this is x, and we have the vertical axis, this is y. Okay, so we have x and y axis. Now as a result, the tension in the cord AC, so let's look at the AC. So this is AC, is T1J. We don't know the magnitude T1, so we just call it tension 1. And certainly there is a weight coming from the load, and it is minus mg, mass of the load, multiplied by the gravitational acceleration, and j, so it's minus because it's downwards. And at point A, sum of the forces has to be equal to 0, and which gives us T1J minus mgj has to be equal to 0. Okay, this is our first equilibrium equation. Let's continue further. Now Next is point C. So let me remind you the C. At point C we have a pulley, and this cord coming from point A turns around it and goes to point B. So certainly the tension in this cord has to be, the cord AC has to be equal to the tension in the cord BC. This is one thing that we need to know, and we call it T1. Now we have tension in the cord from C to B and tension in the cord from C to A, and their magnitude has to be equal to T1. That's okay. Now certainly we have a tension from C to D, and we call this TCD. Now let's write the forces. We already know the TCA. It is minus T1J. We can easily say that. Now TCB, it has to be equal to T1 minus 5 divided by 13I, because this is the component in x direction and it is in negative x direction. So as you remember, this is 5 and the vertical component is 12. So, and again the y component is in negative direction, so it is minus 12 divided by 13. As a result, this is my unit vector from C to B. Okay, so we know the TCA. Let's write the force tension in the cord CD. Let's say that its magnitude is T2. Okay, as a result, T2 is equal to, so remember that this angle is theta. CD makes an angle of theta with the horizon or x-axis. As a result, it is T2 multiplied by cosine theta I vector and plus T2 multiplied by sine theta J vector. Now at point A, sum of the forces has to be equal to 0. This gives us this expression. T1 has to be equal to mg. Now remember that we don't know the mass yet, because this is what is asked to us. And in fact, we don't know the tension in the cord. They are related. Now for point C, at point C, sum of the forces has to be equal to 0. Therefore, TCB plus TCA plus TCD has to be equal to 0. Now this gives us this expression, minus 5 divided by 13 T1 plus T2 cosine theta, we don't know the theta as well, plus T2 sine theta minus T1 minus 12 divided by 13 T1 has to be equal to 0. So this is 0 as well. This expression. Okay. Now, if we look at the our equations in general, we have 3 equations. So this is our first equation. In fact, the coefficient of the I vector at point C has to be equal to 0. And sum of the forces at point C in y direction has to be equal to 0 as well. Okay. Now we will go step by step. So remember that T1 is equal to mg. Now let's assume that T1 carries the maximum load. Okay. So the maximum value for the T1 tension in the cord 1 ACB is 500 newtons. If we put 500 newtons in place of T1, what we are going to get is 50.97 kilograms for the mass of the object. Now let's check whether it's okay or not. Now remember the equation 2. So this is our equation 2. And if we look at the x component, now we know T1, we assume that it is 500, and therefore we can calculate T2 cosine theta from here. In fact, we will substitute T1 here. As a result, we can obtain this expression from here. So cosine theta is equal to 5 divided by 13 T1 divided by T2 from equation 2. So from this equation, from the x component. And if we say that T1 is equal to T2, so they carry the maximum load, cosine theta will be equal to 5 divided by 13, and sine theta will be 12 divided by 13. Okay, this is one approach. So both cords carries the maximum load. Let's check the equilibrium in y direction, because equilibrium in y direction has to be satisfied. Now T1 sine theta minus T1 minus T1 sine theta. Okay, so T1 is equal to T2, which is equal to minus T1, and it is different than 0. Therefore, this tells us something. T1 cannot be equal to mg because it's not 0. Okay. Now, let's look at the case 2. Go further, and let's don't make any assumption on tension in the cord, and we know that T1 is equal to mg, and let's substitute mg in place of T1, and we don't know the mass yet. So it's minus 5 over 13 mg plus T2 cosine theta. This comes from the equilibrium in x direction, remember. And from the equilibrium in y direction at point C, we have T2 sine theta minus mg minus 12 divided by 13 mg, and it has to be equal to 0. Now we have two equations, and we have two unknowns. We don't know the theta, and we don't know the T2, but we know that they are coupled. Now, for the moment, let's assume that T2 carries the maximum load, which is 500. So 500 cosine theta has to be equal to 5 divided by 13 mg, and that's equal to 500 sine theta. So now I put 500 here. Sorry, this is my first equation. So this equation is this one, and this expression is this one. Okay, 500 sine theta, 25 divided by 13 mg. Again, when I look at these equations, I have two constant terms on right hand sides. So I can divide either of the equation to the other one. This will eliminate the mg from my equilibrium equations, and I will be left with theta only. From here, so if I divide this expression to this one, I will be left with tangent theta is equal to 5. From here, I can easily obtain that the theta is 78.7 degrees. Now, I know the theta, and I can use any expression, any equation. So either this one or this one. I already assume that T2 is 500. So if I substitute, I take one of the equations. So I just take the equilibrium equation in x direction. I will find this expression 5 mass is equal to 13 T2 cosine theta divided by 5g from the equilibrium in the x direction at point C. And I will substitute the values into their places. 13, tension in the cord is 500, cosine 78.7 degrees divided by 5 multiplied by 9.781, it is the gravitational acceleration, and I find the value for the mass, the maximum load, as 25.98 kilograms. Certainly, if I multiply this with 9.81, I will see that it is less than 500 newtons. So therefore, T1 is also smaller than 500 newtons, and T2 carries the maximum load in this case.